Hi, everyone. My name is Maya Boyd, and I'm an undergraduate at the University of Chicago in the CDAC Summer Lab program. I'm honored to be introducing Dr. Marynia Kolak, the Assistant Director of Health Informatics and Lecturer in Geographic Information Science at the Center for Spatial Data Science. Dr. Kolak won the Academy Health's Concordium Award for Innovations with Data in 2017 for her web application and open spatial technology framework on healthy access, healthy regions. Dr. Kolak has made a name for herself as an expert in the fields of health geography and data science through her novel discoveries in how place impacts health outcomes in different ways for different people, and her applications of geocomputational methods and quasi-experimental policy evaluation techniques. Today, we're going to hear Dr. Kolak speak more in depth about her contributions to data science. So please join me in welcoming Dr. Kolak to the Summer Lab Speaker Series.
Thank you so much for that fantastic intro. And I did have slides. Can I go through slides? Does that work? Okay, perfect. It's just easier because then I won't. All right, let's kick things off here. So, all right, so I'll be talking a little bit about the work that I do and that the kind of growing lab at our group does. But all of it kind of revolves around the central concept of connecting health and place with spatial data science. So first, to give a little bit of a background of what how my perspective has kind of emerged as spatial over time. I don't have a direct path by any means to where I'm doing what I'm doing today. My background was actually in geology. So my senior thesis related how the ocean floor formed in a part of the micro tectonic plates off of Easter Islands. And my first job actually out of undergrad was working as a climate change scientist intern at the USGS, looking at how microfossils can be tracked to track climate change. Later, I actually got a master's of fine arts in writing, where my thesis there really kind of focused on the history of pre-1833 Chicago, and also had done a little bit of travel in Central America through that, but always still this kind of focus on place, from either geology to kind of even more artistic perspectives. And then later, kind of this love of both communications as well as databases, which comes from geology and connection to place. I ended up working at the Northwestern Institute for Public Health. And there, that place really served as kind of an incubation for me to delve into what I was interested in even more. This eventually kind of, this exposure to public health was really fascinating to me because it kind of combined all of the messy, complex factors that exist of how, the intersections of place and much more. So long story short, this went from, I formalized these interests with a couple geography degrees, and throughout also kind of continued volunteering efforts. Okay, so I really present the spatial perspective as a data science framework. The spatial perspective impacts both the theory, methods, and technological infrastructures of data science. I kind of then triangulate from there to kind of look at how can a spatial perspective inform research design, usability design, and infrastructure design. And these principles will kind of go throughout my research. I really am interested in the question around how does place impact health in different ways for different people. I'll use a wide range of different techniques, from the exploratory data analytic approach that emerged from the beginnings of the computer statistical movement back in the 50s, 60s, and beyond, as well as this applied geographic data science paradigm. I'll also use kind of classic spatial econometric and quasi-experimental techniques when I'm doing policy evaluation work, and then most importantly, open science tools. I use all of these to investigate issues of equity across space and time, and it's really important to me that all the work that I do has some kind of policy-driven system integrating solution at bay. To give you a little bit of a background on what the social determinants of health are, I'll give a definition in just a second, but first, the impacts of the social determinants of health have increasingly dominated the public health discussion in the US, as it's become more clear over time that population health outcomes have not kept pace with other developed nations, even though we spend a lot more money on it. So there's not just an inefficiency happening, but something potentially a little bit more complex. And the more that we can understand SDOH, the better we can not only link patients with social services and clinical contexts, but at a more macro level, which is what I'm really interested in, target vulnerable populations with health improving social policies and programs. And this impacts the this massive goal that's just getting more important as time goes on. We're interested in closing the increasingly widening gap of health inequity in the US. And as you can imagine, this was true pre-COVID, and it's even more true post-COVID. So the social determinants of health are defined as the physical, social, environmental conditions in which people are born, grow, live, work, and age. So as you can imagine, that's basically everything. And it's actually, I'm really interested in how can we actually quantify that, and how do we distinguish how so many of these conditions actually interact with each other. So can we really separate education, work, living and working conditions, unemployment, and so on and so forth. There's a lot of different conceptual models out there that suggest how your these SDOH indicators impact premature mortality, but they're not all in agreement. So never trust a graph just because it looks pretty. So just for example, looking at socioeconomic and environmental factors over here, this model says it constitutes 20% of your impacts. This one about 40% of your impacts. This one 23%. The one on the right looks like it's the most complex, but this is actually the only one that was not generated by a health team. A group of designers made this, so it looks beautiful and detailed and authoritative, but it's actually the least one among all these others. And within this public health space, there's this continued focus on place. So kind of a classic perspective is the most important 5-digit number needed to predict your health status is your zip code, bar none. But that's actually really complicated because of issues of geographic correlation. If there is an association with your zip code, does that suggest a causal relationship? Probably not, right? Because we know that people, we know that it's a little bit more complicated. So our group kind of looks at this from multiple different perspectives. We look at how the kind of core concepts of SDOH are drive a lot of our questions, but then I'm also interested in specific case studies. So for physical environments, let's look at air quality and access to fresh food specifically. How can we effectively model access, or model not just access, but in the case of air quality, model small area estimates, and how does that then interact with SDOH to impact health outcomes? And then from risk environment perspectives, how do social, economic, and policy factors impact both the opioid epidemic and then more recently the COVID pandemic? Because these are really big questions, it really necessitates this more kind of systems framework perspective. I just have a few minutes left, I think maybe 2 minutes, so I'll just quickly do some highlights of 2 projects. So one where we quantified SDOH in the continental US. This was with the American Hospital Association. So we essentially did a cross-sectional observational study looking at multiple health or social determinant of health variables. We did that for the entire US. So looking at all census tracts in 2014 to determine how can we collapse 14 plus variables into some very distinct dimensions of social determinants of health. And then can we validate that in Chicago, looking at premature mortality data and violent crime data. And all the work that our group does is open source or open source adjacent. So all the spatial analysis is in R, sometimes Geoda, and then the product of the final map was published in Carto. So phase one, we had essentially first a conceptually driven model of what social determinants of health are that kind of drove what variables we included. That was a really critical component to kind of build on the previous literature in this area. Then we used a principal component analysis to collapse 14 variables into 4 indices, and those 4 indices explained, I think, almost over 70% of all variation across tracks across the entire continental US. Then we did a regionalization analysis with k-means to develop specific dominant typologies. And then again, I had talked about previously the validation part. So long story short, the 4 dominant components did make a lot of sense. The first one was essentially the classic poverty measure that we're all familiar with, deprivation index, that sort of thing. But we also found additional indices that were kind of super interesting and easily kind of overshadowed by that first component. And then we found 7 regional typologies that varied dramatically, and that in Chicago, over 65% of the variation in premature deaths in Chicago could be explained by SDOH alone. And then my last 15 seconds, the US COVID Atlas project is the most recent extension of some of these similar concepts. We are essentially providing access to county level surveillance and statistical hotspots on a daily basis, and linking in dozens of additional variables that make sense. And as you might expect, we have found several very vulnerable areas that resulted from a variety of factors of COVID. These areas we have unfortunately detected months before other groups. So for example, rural areas and the historic Black Belt have been hotspots since the end of March. So that was another thing that was uncovered. So thank you so much. I'll stop there at 30 seconds over.
Awesome, thank you, Marynia. That was perfect timing. Okay, so now I'll hand it over to Chibueze, who's going to do the next introduction. We're going to hold all questions till the end, actually, in case people have questions. So students out there, please write down your questions as you have them, and then we'll come back in about half an hour.
Okay, thank you, Kyle. Hello, everyone. My name is Chibueze Amanchukwu, and I'm a high schooler at George Bush High School in the CDAC Summer Lab program. I'm honored to be introducing Dr. Chibueze Amanchukwu, the Neubauer Family Assistant Professor at the Pritzker School of Molecular Engineering at the University of Chicago. Dr. Amanchukwu has made a name for himself as an expert in the field of electrolytes and batteries. Dr. Amanchukwu has been recognized with awards from the American Chemical Society for Excellence in Graduate Polymer Research and the American Institute of Chemical Engineers for Sessions Best Paper. He is also a recipient of the 2020 Artificially Intelligent Electrochemistry Grants. Dr. Amanchukwu has won awards for being the best big brother I could ever ask for everything he's done for me after attending the CDAC Summer Information Session in my place. Today, we're going to hear Dr. Amanchukwu speak more in depth of his contributions to data science. So please join me in welcoming Dr. Amanchukwu to the Summer Lab Speaker Series.
Thank you, Chibueze. That's very cute. Okay, let me get this going.
That's probably the best introduction you'll ever get, isn't it?
It really is. And I did not know. I thought it would be cute if that was done, but I did not tell him what to say. Just let's be clear. So thank you, Chibueze. So this is I have my 10 minutes of fame, as Katie said. So I'll try to go through a little bit in detail on batteries and look at opportunities that data science can afford our field. So this is my name, Chibueze Amanchukwu. I'm trying to design next generation batteries using data science. So this is my academic travels, just a little bit of who I am and where I'm from. So was born and raised in Lagos, Nigeria, and then me and the family, Chibueze included, all moved to Houston, Texas. I did my Bachelor's of Science in Texas A&M in Chemical Engineering, Actually did a lot of internships at refineries, trying to, for different purification of crude oil products. But moved to MIT to do PhD, and that was when I switched to working on renewable energy technology, so working on batteries. Then from MIT, went to Stanford for my postdoc, and I completed that last year. I did a short stint at the University of Cambridge last year, but here I am now at the University of Chicago. So I'd like to start with this slide. I think it gives some context to why we are motivated about the work that we do. One of it is that we do know that climate change is happening. So we have regions that will experience more flooding than usual, experience droughts, wildfires, etc. But actually what is not a significant focus is not put on is that the consequences of climate change will also be unequal. And so this is from the Climate Impact Lab here at the university, where they've, so what you're looking at here, red is bad. So that's the higher mortality rates that is expected due to consequences of climate change. And this is a model, so there are some that will be wrong and some that will be correct. But what you can see is the area of the world where I'm from, and some areas, for example, in the Middle East and the Indian subcontinent, are kind of predicted to have the worst of the effects of climate change. One part of it could also be the inability of some of these countries to deal with some of the financial implications that climate change will induce. And so this is a big motivator for our work and trying to see how we can come up with solutions to help alleviate these concerns. One pathway is electrification. So that means instead of burning gasoline for transportation and instead of using coal and natural gas for electricity generation, can we move to renewable energy technologies? So that could mean going from coal. So this is a coal plant in Indiana that used to supply power to Chicago. Can we move to a wind farm? And this is a picture from one in Iowa, for example, that could also supply electricity to Chicago. And I own a Honda Accord. Can I stop using my Honda Accord that is powered by gasoline and instead move to a Tesla Model 3 that uses batteries? One of the rate limiting steps in the development of both this and this is that you need actual batteries because the wind is not always blowing, the sun is not always shining. And also if you want to move your car from point A to point B, you need a portable source of energy storage. And that's where batteries come into play. So this, I'll spend a little bit of time on this slide because if I lose you on this slide, I've lost you for the rest of the talk. So this is an internal working of a lithium-ion battery. So this is the battery that is in your phone right now, that is in your laptop, etc. So how does it look? So if you focus on the left-hand side here, first of all, so this is called, a battery is typically described by 3 components. There are technically more than that, but there are 3 dominant components. So one is your anode. So it's called the negative electrode. Another is your cathode. So this is the second part. So these 2 combination really determines what voltage you can expect from your battery. And then in the middle is what is called an electrolyte. And this allows transport of lithium ions back and forth. So when you connect your phone and you're playing Fortnite or you're watching Netflix or YouTube, what's actually happening inside your battery is that you have lithium ions, these green dots here, that move from your anode to your cathode. And so whenever that is done, an electron goes to power your device. So when you charge your battery, you take these lithium ions that were here and you move them over here. So it's this intercalation, so coming in when you charge and deintercalation coming out when you discharge, that allows you to have a rechargeable lithium ion battery. So what are some of the components of these batteries? So an anode, for example, in your lithium ion battery is made out of graphite. And so think of pencil lead and just like, scrunching all the pencil lead to make a fine powder. And if you look at this under like an electron microscope, you would see that you have all these graphene layers here that allow lithiums to come in and out. For the electrolyte, it's just think of something that's salt dissolved in something. So that could be water, it could be a solvent. So this is a picture of the ocean. It could be Gatorade. All of those are electrolytes. For battery systems, we tend to focus on organic solvents. And then the cathode is tends to be an engineered material, so something like has lithium cobalt oxide or transition metal oxide. So this is how a lithium-ion battery works. But if we want to really effect change in how much energy we can store using renewable energies, how much our car can go from point A to point B, there are a lot of challenges, which also leads to opportunities that are facing lithium-ion batteries. So one of which is how can we store more energy for the same mass? So look at where we are right now, so lithium-ion. And on the y-axis here, you're looking at something like this, so watt-hour per kilogram. So all it means is amount of energy I'm storing per mass, so nothing fancy. But what we want to do is, can we increase this amount of energy that we can store per mass? So this is a chemistry that I worked on for about 5 years during my PhD. But yeah, this is the first point. Can we store more energy? The second point, can we make it cheaper? Cheaper means there's greater access to this technology. So not only the developed nations, but also the developing ones will have access to this. Can we make it safer? So this is a Samsung Note 7 from about 3 years ago that was catching on fire because of the flammable electrolytes that are in the battery. And then another one that is kind of growing in importance, and it should be, is also, can you make it recyclable? So this is our lab, and this is what we care about. We're interested in developing electrolytes. The reason for that is they really allow you to control what is happening at your anode and your cathode interfaces. So this is the workflow that we think about. So one is, can we use data science as a way to generate new ideas for compounds that we should make? So that's starting here. So people have been working on batteries for over 2 centuries, right? So there's a lot of literature that we can learn from. If you give me 2 compounds that I know that maybe it kind of work, can your algorithm tell me the one that will be best or optimized? And then in our lab, we have the ability to make them, characterize them, right? And look at them using calorimetry, look at them using different spectroscopic methods. And then we also can put them inside the battery and test how the battery works. So it doesn't have to be linear in this way I've drawn it, but this is one way to think about our research interest. So I'll focus on one of the projects that I did. And I know I don't have too much time. I was trying to make this, I would love to get your comments at the very end for Q&A. But one of the questions that we wanted to solve in this work was, typically there's always a give and take with electrolytes. So for example 1, you have an electrolyte that is ionically conductive. So that means it can allow lithium ions to go back and forth in it. But once it touches your cathode, remember the cathode we talked about earlier, this compound tends to degrade. So that's why I've shaded this red. But if you find this compound, people have studied it heavily and saw that, wow, it's very good when it's in contact with the cathode, but it actually doesn't conduct ions at all. So it's of no use. So when I was thinking about this problem, and this is a human being sitting down and thinking about it, I was like, oh, well, can we just mix them, right? So yes, you can mix them, but the issue is that this compound still has access to the cathode, and so it doesn't actually work if you mix. The oxidative stability is still quite poor. So one of the approaches that we did in this work was to actually go into the lab and synthesize a new compound. So if you look at this new compound here, so just draw your attention here, you look at this component, looks a little bit like this. So that gives us a stability part. So we have a check mark for stability. And then this end looks quite like this. So that gives us the conductivity part. And so we're able to study this and show great ion conduction. But just after our work was published, so I spent a year working on that project, designing different types. Just a year after our work, or just 2 months after our work was published, I ran across this paper. And what does this paper do? So this paper, they try to predict, using the model that they've developed. Here was a linear free energy system, not necessarily machine learning. But what they were able to do was, if you look at these open circles, they're able to very much predict my compound. And I'm sure this did not take them more than a day to do that. If I had this information, I would have actually made this one instead, because they were able to show that if you change this internal structure here, so what's the difference? So remove all these oxygen groups here and make it somewhat like this, you would actually see significant jump in conductivity. That's the blue dots. And so my colleague was actually able to make some of these at Stanford, and so we're able to show that these compounds have higher conductivity. But the reason I show that is that's just within the electrolyte space. In batteries, I've told you that you need to have a combination of the anode, cathode, and electrolyte, and there is a whole suite of compounds that you need to mix and match. So with that, some of the questions that data science can help us solve: new materials prediction. Can I know if it's promising before I make it? How can I compute the properties much quickly and accurately? And if you've told me a great compound, can I just have a robot make it for me instead? And then once that robot has made it, can I have an algorithm that can help me characterize and understand my data more easily? So with that, I've run out of time. So reach out to us if you have any questions. You can also tweet at us if there's anything, if you have a Twitter account. And with that, I'll end.
Awesome, thank you. So your goal is to automate yourself out of the process completely, is it?
Basically, as long as I get all the patent rights and I can actually make money out of it, then yes.
As long as you get the patent right. I love it. Okay, that was awesome, thank you. So we'll turn it over now to Ryan, who's going to give the last introduction, then we'll go on to Q&A after Bryan's talk.
Hi everyone, my name is Ryan Wong and I'm a high schooler at Whitney Young in the CDAC Summer Lab program. I'm delighted to be introducing Dr. Bryon Aragam, an assistant professor at the Booth School of Business at the University of Chicago, as well as a Topol faculty scholar. Dr. Aragam has established himself in the fields of mathematical data science, statistical machine learning, and non-convex optimization, and has had his work published in top conferences and venues, such as the International Conference on Machine Learning and the Journal of Statistical Software. Dr. Aragam was also recently awarded an NSF grant to research a new approach for learning directed acyclic graph from data. Today, we will be hearing Dr. Aragam speak more in depth about his work in the intersection of data science and business. Please join me in welcoming Dr. Aragam to the Summer Lab Speaker Series.
All right, well, thank you for the kind introduction. Can everyone hear me? Get a thumbs up. All right, great. So let me go ahead and share my slides. Where are they? Here we go. And hopefully everyone can see my slides now. Thanks again for the kind introduction and thanks for the invite to chat with y'all. There's a limited amount of time, it sounds like, so I'm going to try to keep things fairly high level. I won't go into too many technical details. But before I jump into sort of some of the details of my research, let me tell you just a little bit about sort of how I came to this style of research and the type of problems that I'm interested in. So I'm interested in applications of unsupervised learning in data science, but my background so my bachelor's was in math, I got a master's in math, and then my PhD was in statistics. So sort of a very abstract, more theoretical background. But along the way, I interacted as a consultant with marketing firms, tech firms, startups, and also a significant part of my PhD involved applications in computational biology, all of which sort of forged this interest of mine in interacting with practitioners and understanding their problems, and then coming back to the abstraction to try to prove things, to make them faster, to make things more reliable, which sort of brings me to sort of the high level motivation behind my research, which quite simply would be to say something like, we want to help practitioners specifically by developing theory and algorithms to improve and explain the methods that they use every day in practice, right? So practitioners have all kinds of really cool tricks that they use to draw inferences, to make their algorithms faster. And we're interested in helping them out in order to make things more reliable, faster, and interpretable. So my day-to-day tends to look a lot like this, a lot of equations, a lot of abstraction, but a core focus of the theory and the mathematics that I work on is to always be able to find end products that look more like this, some type of deliverable that we can hand off to stakeholders in order to be able to make actionable decisions and have positive outcomes using whatever data it is that they've collected. So I'll talk a little bit about a couple of these applications towards the end, but let me tell you a little bit more about sort of the high level behind the problems I'm interested in. So kind of the idea in unsupervised learning is you want to start with some sort of unstructured, complicated looking data like I have up in the left. Actually, this is more structured than a lot of the data we look at. But we want to take data sets like this and transform it into something structured that we can draw inferences from and draw conclusions from. So taking something complicated and producing some sort of concrete object that we can talk about what's going on inside of this data. So some of the applications and some of the problems that we focus on include causal inference, representation learning, fairness, interpretability, and explainability. So this is a really important problem that's come up recently with the applications and implementations of machine learning and AI in business and industry. And then other examples, I'll talk about personalized medicine, complex networks, and also time series and dynamic models. But at a sort of the most important thing is the question that sort of unifies all of this is how do we learn some type of context and structure from various types of large unstructured data sets? Okay, so that's one of the goals, but there's also a second component. So part of the rise of the popularity of machine learning and artificial intelligence over the past few decades has been due to these very successful, very accurate, but very complicated models, such as deep neural networks, that are able to produce accurate predictions, but at the same time, especially recently, have come under criticism for a lack of interpretability, safety, and reliability. So figuring out how to integrate these things so that you can have accurate, complex predictive models, while at the same time ensuring robustness, safety, and interpretability is sort of a crucial goal to sort of put these two things together. So some of the questions that we're interested in are things like the following. So how do we build systems that can explain the decisions they make and explain the outcomes of their predictions? And how do we build systems that are able to adapt to individuals and their preferences? So instead of just being able to make good predictions on average, can you make decisions for individuals that adapt to their specific preferences? And also, is it possible to build systems that are capable of identifying their own failures? So instead of sort of always trying to give you some type of output, to be able to say, well, I don't know, or, you know, it's very likely that I might be wrong here. So these are the types of questions that we're very interested in trying to sort of build theory for, but also have practical software and algorithms for answering. So I'll talk real quick about a couple applications. They're going to be very different, but don't worry, I'll tell you how they're related in the end. So the first one is a more applied project involving personalization and pan-cancer modeling. So the basic idea here is cancer is a very complex disease. Each patient is very different, even though they might present similarly. So at a molecular level, these distinct mutations in the genetic code can present very similarly in a clinical setting. So we want to be able to understand the genetic basis of cancer and also to be able to make personalized treatments, but without sacrificing interpretability and without sacrificing data. So what do I mean by this? We need interpretability so that doctors and clinicians who use these methods know that the predictions that are being made are reliable and sort of in line with what the science says. We also need to make sure that we're using as much of the data as possible. So if you look over at this table I have, you'll notice that this is a list of a bunch of different types of cancers in a large data set that we used on this project. And you'll notice that several of the types of cancers have, over 1,000 different cases. But down towards the bottom, there are things like eye cancer, lymph node cancer, and bile duct cancer, for which there are very few cases. And now if we were to simply treat these conditions distinctly, then we wouldn't be able to understand something like bile duct cancer very well because it has a very limited number of samples. But of course, at the same time, we know that there's a lot of similarity between different types of cancers in spite of their differences. So is there a way to use all of this data, to use all of the power in these large databases to build personalized models that don't sacrifice predictive ability while still being able to understand sort of the nuances of the individual cancers? So to do this, we built these personalized models where we had one model per patient using all of the data from the cohort. I won't go into the technical details of how we did this, but just to give you sort of an idea of what this looks like, one of the sort of things that we discovered was, so here, each row in this figure here corresponds to the gene expression data for a single patient. And the color coding corresponds to the type of cancer. You can see that coded over on the right. And this is a cohort of a few hundred patients that presented at a molecular level very similarly. But you'll notice that they were not coming from the same tissue type. So essentially all the different types of cancers were represented here. And the idea was by looking across the different types of cancers and by borrowing strength across all of the patients, we're able to understand these sort of finer grained molecular subtypes that arise in cancer studies. So this is sort of a well-recognized phenomenon at this point. So that was one project in personalization. I'm going to pivot really hard and talk about a more theoretical problem, but that has really important practical applications. So this is a problem called semi-supervised learning. And in this problem, the idea is that you want to make some type of predictions. And what you have, instead of having a lot of labeled data, what you have is a lot of unlabeled data. Okay, so you have a very small amount of labels and you've got a ton of unlabeled data. So this is a very practical problem that arises particularly in industry where labeling the data can be very expensive. And here we want to be able to use this unlabeled data to make better predictions, to extract useful information, and then most fundamentally to actually be able to prove that we've done something useful. So this has always been a challenge in these types of problems where there are lots of empirically validated methods that seem to work well, but we don't fully understand their flaws and their merits. And so if we can actually prove something mathematically about how you can leverage structured representations from unlabeled data in order to make predictions, that's really useful, right? Because now we understand the flaws and merits of the system. So I won't go into the details of how we did this, but I'll just mention a couple of the sort of interesting mathematical tools we used, including non-parametric statistics and the Wasserstein geometry of probability models. So the idea here was to be able to answer some very precise questions about a very practical problem. Now, these are two very different looking problems. But what I want to emphasize to conclude, I can see I'm running out of time here, is that these are actually the same problem. What this boils down to is learning a structured representation from unlabeled data. And this is useful for a wide variety of problems. So I mentioned personalization and I mentioned semi-supervised learning. A couple other projects that we're interested in, so causal inference and graphical modeling is a very important one. Fair prediction, so I mentioned this briefly, and several others, many more that I won't mention here. But this is just sort of a quick overview of the type of problems we're interested in. And if anyone has any questions, please let me know. Thank you.
Well, thank you all. That was amazing. I can't believe, one, how the quality of the presentation, but two, how well you guys did with time. That's quite exceptional for 3 people to actually finish that quickly. That was awesome as well, the end there, Bryon. I think there's a lot of opportunities for that sort of work, and I'm sure Marynia and Chibueze, you also see opportunities. I know Chibueze in some of the labeling work of extraction, text extraction, there's a lot of opportunities for that type of approach. So I'll turn it over now to the audience for questions. These questions, of course, can be related specifically to any one of these projects, or they can be more general about sort of the interesting applications of data science and domain science. Before I pick on people, someone unmute themselves and ask a question. Okay, I'm going to go through the questions that have been pre-posted and pick someone. Ray, would you like to ask your question? Is Ray here?
Yeah, I'm here. 1 second. Yeah, so my question is, what is the most surprising thing you've learned or discovered through your research?
I see some blank faces, lots of things that I've discovered. They're trying to rank them. Most surprising. Go ahead.
So something that is kind of a rule in my field, that things are you know, everything will be different depending on where you are. That, you know, so for example, when you're looking at a policy or just a social phenomenon, the impacts of that will vary so dramatically for different populations. So for example, the impacts of pollution can actually be greater in one area versus another area for a variety of different reasons. And I'm just always kind of blown away at the complexity of all these different components, and just the need for great thinkers in interdisciplinary fields, right? So air quality is essentially looking at how air moves through the air, which requires some knowledge of fluid dynamics and really complex chemistry, and much more. So that's true. But on the other hand, there's other phenomena that are so persistent and stable, irregardless. So for example, in the US, we find that the impacts of segregation and kind of structural racism persist, even though that's not necessarily what we set out to study. In almost every single topic our group has looked at, from the opioid epidemic to COVID, to the impacts of air quality or food access, we see how pervasive structural racism is in impacting the results. So I think that's two things that can be very frustrating for many different reasons.
I guess I can go next. I think the most surprising thing is, even though you might think working on batteries and energy is very different from working on drugs for cancer, for example, is that they're actually very, very similar. So we tend to be, as a field, like behind what people have already done. So even in data science, a lot of the tools that we use for data extraction, people have done that in linguistics, for example. For a lot of how we represent our molecules for materials data science, people have done that for drug discovery because it's of great interest to them. Even some of the techniques that they use to characterize their drug molecules, they've started to encroach our area. So one that was really famous recently was the use of cryo-TEM, so transmission electron microscopy, to study cells. So cells are very sensitive to the laser that you try to use to excite them or to get an image. And so if you cool them to cryogenic temperatures, then you can easily study them. And it was only until 3 years ago or 4 years ago that technique was used to study battery materials, even though the problems are exactly the same. Battery materials are very sensitive. So I think what I've come to appreciate more is to actually be aware of what other people are doing in other fields that might seem so disparate from yours. And there is so much information that you can mine from that. So that's quite helped me in my work, and it's been a good surprise.
I think I kind of just have to second everything that's been said. I mean, I think the complexity of the problems, but also somehow the amount of structure that's in these very complex problems, I think is really fascinating. You can start with a problem that just seems kind of hopeless. And I think The cancer example that I talked about is one of them. It just seems like such an intractable, such a complicated problem. You know, even the fact that different types of cancers can present similarly. These things, you know, I find this really fascinating. And yet at the same time, there's still some level of complexity behind this all. So it's this sort of tug of war between trying to appreciate and model the complexity of the problem, but also understanding that a lot of these things are really closely related and that you can borrow ideas from different fields, even subfields within the same field, as well as, you know, sort of all over the place, has always really fascinated me. And this is one of the reasons I really love interacting with practitioners, is that you know, the amount that I learn from them is just mind blowing, right? So even when I'm working on theory, I can get really crazy ideas, really interesting ideas from talking with practitioners. So I think that's probably been the most surprising thing to me.
Awesome, thank you all. Okay, back to the audience for the next question. Keep lining these questions up.
Yeah, I have a question.
Thank you. And I should say thank you, Ray, for that first question. That was excellent. Sorry, go ahead, Ryan.
How easy or hard was it to get into data science, given that you all mainly work in other fields?
I can try to start on that one. I think it was kind of accidental. Data science kind of started to become a really big thing as I was starting my PhD and progressing through, and I was always interested in sort of the intersection between like artificial intelligence, statistics, and machine learning. And then that kind of over time evolved into data science. And I think it was almost by accident that I just kind of was in the right place at the right time, working on the right things. And so I'm very thankful for that. But yeah,
I guess I can follow. So I think I'm an experimentalist through and through. And so my biggest rate limiting step is always I need an idea for a new compound to make, and then I can go into the lab and make it. So I stumbled across a paper, I think last year, that was published last year, 2 years ago, where they just used natural language processing and Word2Vec and scanned the entire literature, and they could have predicted what material would have been made in the next 5 years or so. And some of those materials were made, and some of those materials showed quite good performance. And I was like, wait, that could make my life so much easier if you can just extract a lot of information that's already there in paper. So I'm not coming up with a new computational model to design something. There's all this literature that's very smart and brilliant people have already made in decades past. And then in terms of getting into data science, it's really that need. Like we really do need the new ideas that we can get from this space. And there are a lot of techniques that are more accessible to us now. So I don't have to do Word2Vec from scratch. I can just plug my data in and see what is the very bare minimum. So as computer scientists come up with fancier models and fancier abbreviations for those models, I just need to take the ones that they've worked on 10 years ago and apply that to my problem. So that's been an easier thing for us experimentalists to get into this space.
And for me, it's interesting because data science definitely it existed, but it wasn't called data science. So I kind of also fell into the field from a accidental or tangential path. And it's interesting too, because there were different points in my career where I wasn't quite sure. Like I knew what I was interested in doing, but there wasn't a kind of a clearly defined name or field or approach for it. But I'm a very stubborn person. So I think that kind of helped push things forward a bit. I think earlier on where there were a few data science specific fellowships or opportunities that came up, I actually was rejected for a lot of them because I hadn't, I think something that I didn't quite appreciate was just how important it is to have your code available as GitHub repos and that sort of thing, right? And sometimes, especially if you're a woman or a minority in the field, at least within the world that I am, it's just persists to be really important to kind of show your work so that kind of discrimination doesn't happen, to shift your approach, and that at that same time to also maintain kind of a persistence and joy in doing what you're doing, and moving forward. And just to note now, like, so some of my friends from my geology days will reach out to me with a really interesting question that requires kind of a machine learning approach. So I can actually borrow that from things that I've learned in the public health field, and pass that on to them. So I think that this common language of computer science, math, innovative thinking that's common to data science is a really powerful way to connect different fields as we continue.
One thing I'd say, just building off of that as well, is that I think this idea that data science as a name is relatively new, but data science has been around for decades, if not, over 100 years, right? It's just in the past 10 to 20 years that this has kind of evolved into a more sort of cohesive, I won't say well-defined, because I think still there's a lot of questions about what exactly it is, but it's sort of been appreciated more. And I think, I think for many of us, we sort of been doing things that were data science related, but it wasn't called data science. And then, for me, for example, over the course of my PhD, this thing called data science like emerged out of nowhere. Even though the work that I was doing day to day didn't change a whole lot. So yeah.
Yeah, that's a really interesting. Oh, sorry, Marynia, go ahead.
No, I was just thinking, because I think now that we have like data science programs, that can be really confusing to students, where I've had students ask me, like, there'll be some of the top students in my classes doing phenomenal things, and they'll be like, I'm interested in data science, but I don't have like a data science degree. Like, is that going to hurt me? Or should I stop?
Yeah.
And I'm like,
it's such a foreign idea. None of us have data science degrees.
It's particularly interesting asking you guys this question, because I think all three of you probably went through your studies as this was sort of evolving as a field. And so you've probably seen the sort of before, middle, and after, or maybe we're not even after. Maybe things are going to keep changing more. So, okay, awesome answer. So we'll turn it back over to the crowd. We've got about 7 minutes left. We can maybe get through 2 or 3 questions. Don't all put your hands up at once.
I have a question.
Chibueze, wonderful. Thank you.
For Bryon, before you came into like your research field, did you know that you would experience like that level of abstraction in your day-to-day?
Oh, that's such a good question. I've literally never thought about that. It's tough to say. So my background started really, really abstract. So as an undergraduate, I did essentially entirely pure mathematics. So it was almost all abstraction all the time. And then sort of kind of got gradually more applied as I got more interested in machine learning and data science. But I don't know back then that I knew that this sort of intersection between this sort of abstract stuff and the sort of practical data analysis would happen. Of course, that was all sort of floating in the background. I just didn't realize it. So yeah, this may be an unsatisfying answer, but I'm not sure that I was aware when it was happening that this is sort of how things were going to end up.
Okay, back to the audience. Great question, Chibueze, thank you.
I had a question.
Julio, go ahead.
So I want to know, based on a previous question about how you got into data science, and I was wondering, like, what impact has data science made in helping progress your research, especially in light of COVID-19, where you may not have as similar access to resources that you may have once had before COVID?
Wonderful question. Maybe Chibueze, that's
I can
one for you.
start with this one. Yeah. So yes, as an experiment, so I started my career here in January. So as an experimentalist, the pandemic has just wreaked havoc in building a lab and getting students in the lab and etc. So actually, it's helped us quite significantly because we spent all the time during self-quarantine just working on, for example, just extracting data from the literature and trying out different ML models. So that's actually really helped us in giving us ideas. We haven't had a breakthrough compound yet, but at least we know where to start looking more in depth. But the pandemic, by forcing us to stay home, kind of made that the only option for my group to work on. So that has been quite fruitful for us. But we're still waiting for the breakthrough compound.
Marynia, Bryon, any other sort of big implications of COVID on your work? It's probably hard to compete with your poor Chibueze's lab being ruined by the pandemic.
I feel bad though, because on our end, things have been so busy, so busy. And it's interesting because I think that because even though I work in spatial epidemiology, I didn't have a traditional epidemiology training. Instead, it's more that what's essentially a data science approach. But that's actually been very essential to how our group responded to COVID and kind of have extended to supporting, multiple other groups across the country through the COVID surveillance work that we did. Because in a lot of fields, there's usually a way things that are done, right? So there's usually a favorite model, or if, epidemiologists love the logistic regressions. Econometricians love their, specific OLS frameworks. But when you work with, from a data science perspective, there's so much innovation and freedom, and you see, you're more interested in like, how can I, adapt the right technique to solve the problem in the right place of the decision-making process, and so on and so forth. So that really allowed us to be really creative in how we address the needs. So our group, what started off as a brainstorming session in early March, kind of escalated very rapidly to generate this atlas for COVID surveillance purposes. And we connected with multiple other research groups across the country as a result. So now we have a coalition. We had funding. Funders actually reached out to us to support, and that never happens, or at least, I'm still relatively in the early side of my career, but I don't, from my understanding, that's not a common occurrence. And just keeping kind of the tradition of open science and collaboration moving forward was really important in how we responded to things.
Yeah, I think it's pretty rare. I'm still waiting for the day a funder reaches out to offer me money. Maybe one day. Bryon, what about you?
So I think as someone who primarily works on pen and paper and on algorithms with computers, I think the impact on research is sort of yet to be determined. But I will say, I think there's sort of the non-research aspects where just, I think we've all been feeling the isolation, the lack of sort of interaction with, it's great to come to campus and see all these fantastic scholars at the University of Chicago and have these wonderful conversations in the hallways and in the quad, but that's not happening now. And I think everyone probably that's sitting here right now can probably appreciate this to a certain extent. I think everyone who wanted to be a part of the summer program and is now at home, right? So I think that, we'll end up seeing what the impact of all that is in the end, but I think we're all feeling that right now, and I certainly can sympathize with what we're all feeling right now.
Yeah, that's a really big point. It certainly impacted this program a great deal. Do you guys have time for one final quick question just to end our program? Yes, I see nods. I'm going to hand it over to Katie for her question. Young student Katie Rosengarten.
Yeah, clearly have a very technical question related to data science. So I selfishly have a question that I would love to hear your guys' responses to for our students who are ending our program right now. And I was wondering kind of what advice you would have for, say, a Joe Schmo student who has finished their time in the CDAC program, is really interested in pursuing data science research, but kind of doesn't know what the next step would be after this program.
Bryon and Marynia, I think you guys can tackle that first.
From my perspective, it's really important to, especially since it's still fresh in your mind, make sure that you're developing a portfolio. There are so many people who are doing data science out there now. It's really difficult to kind of assess student A versus student B, either for research opportunities here at UChicago or for kind of jobs beyond and that sort of thing. So it's really important to, and that is kind of administrative work, right? But that's also another part of being in this field is kind of managing your own portfolio. So that could be a website, that could be a GitHub repo or some connection of that. I think all those speakers today did such a great job. I'm always super inspired and shamed by the amazing ways of communicating the research that other folks are doing. So that's really important. And then the other part is find a passion project. And if a student emails me and says, like, you know, can you put me on something? I want to learn more. It's going to be hard to, that's going to take a, you know, if I do give you a job, it'll be excruciatingly boring, right? So versus coming up with your, like, what drives you, what questions are you interested in, you know, until you find a spot of some, you know, either again through research or jobs later, kind of hacking on your own project and sharing that is highly recommended.
Yeah, I think Marynia stole everything I was going to say, basically. Keep doing it. Don't stop doing data science. And one of the beautiful things about data science is it is something that you can do on your own laptop at home. And I think to get yourself to keep doing it, again, stealing from Marynia here, that find something you're really passionate about or something that you need the answer to. So I'll give you two examples that I've used in the past. So back when I lived in California, I used to surf a lot. And my friends and I were always interested on when the good surf days would be. And we collected data on this and we built models. And it was all very rudimentary, but it was actually very practical for us. And it proved really helpful. More recently, I was looking for an apartment in Chicago, and we've all been isolated. And I just recently moved here, so I haven't seen as much of the city as I wanted to. So I got some open data off the City of Chicago website and learned a little bit about the different neighborhoods in Chicago. These are all things that, you know, the data is there. Just get the data and find something that you're really interested in. And it doesn't have to be fancy. It doesn't have to use some crazy complicated model or some huge data set. If it answers a question that you're interested in, then you're doing data science and you're sort of helping to sort of develop your skills. So that's what I would suggest.
I guess the final thing, so coming from an experimentalist point of view, there's always this dichotomy between an experimentalist who knows material science and batteries, and then there are computer scientists and data scientists who know data science. And there's often a lag in the middle of people that can kind of interface both worlds. And so as you leave the program and you understand in data science, your passion project that you pick, it may be in biology, it may be in material science, and the ability to navigate both of them is very, very enlightening, both intellectually, financially. There's a lot of opportunities in both spaces and being able to act like a translator between both. So yes, understand data science. Pick a domain that you think it's very exciting. It could be climate change, it could be batteries, it could be health, and also learn some of the intricacies of that. And you'll be able to have conversations with both sides and be quite fruitful.
That is an absolutely perfect way to end what I thought was an amazing final seminar, our 11th seminar in the series. So thank you, Marynia, Chibueze, and Bryon. I'm sorry about pronunciation, Chibueze. One day I'm going to get it spot on, but it's still a work in progress. Thank you guys a lot for sharing your time with us today. We really appreciate it. Those talks were amazing, and I think they're inspiring for the group of students we have here.